Okay, so lesson 3 takes a more in-depth look at the resultant of things. Today we're going to look more at applications of it. So we said yesterday when we add forces together, if they're going in the same direction, we can put them together and add them in tandem, like this first one here. This person's pulling with 6 newtons force, this person is pulling with 4 newtons force. All together we have 10 newtons of force. But most often we don't have things pulling in tandem, we have them pulling at an angle to one another. So in the second diagram, the 6 and the 4, thinking about the idea of completing our parallelogram, we do this, and we do this, and we know that where the tails join and where the heads join is our resultant force, right? That happens lots of times when things can't pull in tandem together. So to solve the resultant, to actually figure out the size of this, not just draw a diagram anymore, we're going to have to know some things about the length of that line and the angle of that line. And we can do that if we draw a picture using vector addition and use some trigonometry to help us solve the angles and sizes of that. Okay. It turns out we work with right angles, north and east and south and west and things like that, we can use Pythagoras and SOHCAHTOA. If we work with things like that diagram aren't right angles, we'll have to go back to cosine law and sine law. Okay. So let's take a look at our first example. We got a plane flying north at 650 kilometers an hour. So it's going this direction, right? 650. So we've got a wind blowing from the west. Okay, so if it's blowing from the west, it's actually going towards the east, right? So like that. And because one was north and one was west, we know these actually form a right angle. And that's 50 kilometers an hour. How fast is the plane moving relative to the ground? So the plane was trying to fly north, it got blown a little bit towards the east, it actually ends up going this direction. And what have I just done? Well, that's vector addition, right? Head to tail, the tail of the first to the head of the last. And I want to know how big this is. So for part A here, the right angle triangle, I can use Pythagoras. 50 squared plus 650 squared will equal x squared. If I put that in my calculator and then square root it, I end up with 651.92 kilometers an hour for x. It's a nice old simple Pythagoras question. For part B, at what angle is the plane's resultant direction? Well, the plane was trying to fly north, right? But now it's gone over this way. So I have an angle here I have to figure out. So go back to SOHCAHTOA, because it's right angled. This is my opposite. This is my adjacent. That tells me I can use tan. So for part B here, the tan of my angle, that's y, equals opposite over adjacent. Right? I want to find the angle, so I'm going to have to take an inverse. So we said when we did this stuff way back when, I take the inverse of whatever that fraction happens to be and punch it in with a dividing sign on my calculator or as a fraction, and I end up with 4.4 degrees. So if I had to write this out in words here, I'd now say, okay, the plane is flying at, we said our speed was 651 right up there. Oh, sorry, a little bit higher. 651.92 kilometers an hour. At what direction? Well, it's not 4.4 exactly. It's at north 4.4 degrees towards the east, right? We turn into a bearing if we can. And we solved that one. If you want to give the second one a try, this would be a good time to do that. We're trying to pull a car out of a ditch. Two tow trucks are pulling with equal force, and they're joined tail to tail. How much force do they have to apply to the car, or what force was being applied to the car? So think about our parallelogram. If I rejoin it and rejoin it, the tails to the heads would be my force, right? And we know if this is 90, then this has to be 90, because those you can't change that, right? They're using the same spot. If I want to find the force, and they're pulling at 90 degrees to one another, and it doesn't tell us that, but I'm telling you that that's a 90-degree angle. I know I can use Pythagoras again. 90 squared plus 90 squared equals x squared. Okay, this gives us 6,200, and we square root that. And how much force is actually being applied? 127.28 newtons. The tow trucks are applying 127.28 newtons of force. Oh, but force should have a direction involved in it, right? So we need to at an angle of, well, let's stop for a second here and think. They're both 90s. That makes it a isosceles triangle, right? If this is 90, what's left over for the two? Well, they're both 45s. And that's a sort of a special situation of 45 degrees. To both trucks. Okay, but remember, force, velocity, anything of the vector needs a size and a direction. Okay, let's move to the back side. Slightly more complicated examples here. Okay, these ones are going to look at things when we don't have forces acting at 90. Okay, whenever we're given two forces that are acting upon each other, they're always tail to tail. So when you're drawing a diagram, start off tail to tail. Knowing that, we're going to have to turn them into a resultant. Okay, so we can use our parallelogram method to solve something. And because they're not 9 degrees anymore, SOHCAHTOA Pythagoras won't work. We're going to have to use the sine law and the cosine law to figure out our sides and our angles. Okay, so I'll do the first one together here and show you how this works, and you can try the last one yourselves. Two forces of 100 newtons and 80 newtons acting at 50 degrees to each other. So here's 100, okay, and we're going to do at 50 degrees. And here's 80 newtons. What is the resultant magnitude? Well, I can't do it the way it is because I have to turn this into vector addition. But if I complete the parallelogram like that, my resultant vector will go right through the middle here up to the top. And we'll call that R for resultant. Okay, now the nice thing is, I've got 100 on the bottom, I've got 80 on the side, and I can use the cosine law if I were to know this angle. So there's one thing that to remind ourselves about first. When we have lines that are parallel, the inside angles are not the same. However, they always add up to 180. We call this the C pattern. Okay, so looking at our diagram that we just drew a second ago, we have a C pattern. Right? Here's the C. If I know this side is 50, I can figure out this side. 180 minus 50 will leave us with 130 degrees. Okay, so that's how I know what this is. Now I'm set up for the cosine law. Okay, cosine law, if you recall, we're looking for sides. So it's a squared equals b squared plus c squared minus 2bc cos a. A's are the important things. A's are the things that matter, right? So in our diagram, this is A and this is A. Those are the things that matter. B and C are interchangeable. Okay, so we're going to get A squared equals 100 squared plus 80 squared. 2 times 100 times 80 times the cos. The angle we figured out was 130. We like the way this is set up. We can put it all in our calculator at one time. Okay, for that, we'll get A squared equals 26,684.60. That's A squared. Okay, so we square root that. Remember, A is our resultant, right? So it's 163.35 newtons. Okay, there's the magnitude of our resultant. In part B, okay, sorry to write this down. The magnitude of 163.35 newtons. In part B, it says calculate the angle the resultant makes with the 100 Newton force. So that's asking me to find the angle, as my resultant, the angle that I make with the 100 Newton force. Find y. To do that, I'm going to use the sine law. I'm going to match up things that go together. For instance, I know 130 goes with the resultant. We just calculated that. And I know that y goes with 80. So I can write down the sine of 130, the angle I know, with the magnitude I just found, should match with the sine of the angle I want to find and the 80 that's across from it. So going back to our sine law here again. We said from day one we cross multiply when we do this. So 80 sine 130 equals 163.35 times the sine of y. We'll divide out the parts that we want to get rid of, which in this case is 163.35. We cannot divide out the sine, right? The sine's attached to the y. So we'll get sine y on this side. On the left side we get this big ugly decimal, 0.3751. But that's okay, because what we're doing with that, we're taking the inverse of it. 0.3751, all that stuff on your calculator. And what do we get for y? Hopefully, you guys end up with 22.0. Okay, so therefore, okay, the resultant makes an angle of 22 with the 100 Newton force. Okay, and you guys may give the last example a try yourself. Same ideas. It'll be in the next video, but give it a try.